it sound reasonable? Nothing yet. Okay. All right. Please make sure you're on the Discord so that we can answer questions in the run up to it if you do have any. The tutors should all be there now. I think there's one still missing that I need to follow up on. But we're there to help. I don't want that to be a big stress, even though we have to do tests. I guess I'm not planning anything funny, let me put it that way. So I hope it's a straightforward test for you guys. It's going to be a mixture of written and quiz this time. So if you're going off of like last year, what happened, it is a bit different. The reason being is that I have found that if we don't do written tests before the exam, then the exam just sometimes goes sideways. For some people like it's fine. But I'm obviously doing like more of a catch-all approach to this. So I've added in written questions. What it does mean is that it's going to probably seem more intense now, but your exam is going to be slightly easier, it's going to also then, your exam will then have quiz questions. So it should then feel slightly less of like a big deal on the day of your exam. So I hope it gives it a little bit more of a balanced amount of difficulty as we go, but we'll see how it plays out. Okay. And then again, I urge everyone to just keep an eye on the project. It is hopefully going to be less, again, like kind of immediate intense work, because it's only 2 pages that you have to write and you're allowed to use LLMs and stuff. But I do just, I urge everyone to just keep an eye on the fact that it is looking for some kind of depth and commentary and thought. If you just go and do the bare minimum of what's described in the outline, you're probably going to get something around 60%. Okay. So if you want more than that, then go do more than that. If you're happy, if you're happy with 60%, then by all means, just do what you feel is best. But there is a trade-off just between amount of writing and time you have to spend on it, and amount of just thought and clarity you need to have. So I'm putting a little bit more tax on just thinking, because hopefully that just means you're spending less time grinding at a computer. Okay. But keep an eye out. We can chat about it. Again, your tutors are there, and we have a Discord server set up so that you can chat to everyone if you need. All right. That's that out of the way. Let's move on to today's lecture. And again, it's the last bit of content that we're going to need for your test. And it should be I think this is probably one of the easiest, if not the easiest lecture in the course. That's not to say that if you're confused, don't ask questions or anything. I'm just trying to say that don't overcomplicate this lecture. You know what I mean? Like, just take it. If you feel like it's easy, if you feel like it's obvious, trust yourself. It's because you've had 4 good weeks and you followed along, and you should hopefully be starting to have quite a bit of intuition for language and modeling. And so I'm going to kind of go through it fairly quickly, just because I just don't think we need to overcomplicate this bit. So let's talk about what exactly a model is. So on the pictures there, you have a model train, right? And so the whole point of this is that it has some properties of a train. It at least looks like one. It's got a cute little chimney-shaped thing off the front. It's got some wheels, and it can behave like a train, right? If I put some force in the front, the carriages or the bits at the back will be pulled along. And so that's kind of the same exact mechanism that a train uses to drive forward. But it's not exactly a train, right? It's a bit of a very crude approximation of all the things that's going on. Clearly, there's no combustion engine off the front of it. And so we can then try and make a better model train. And so while it's still not a train, it's still got no combustion happening in the front, at least now this one has more of the details. It looks more realistic. It's got the same paint. It's got the same kind of tracks now. It's not on wheels. It's on actual tracks. And so now this is a better approximation of a train if we're trying to understand trains. And this idea is becoming prevalent across. Am I recording? Yeah. This idea is becoming more and more prevalent in machine learning in general in recent, months, years. You've probably heard guys like DeepMind and stuff talking about world models. It's the same idea, right? It's some aspect of. It's something that imitates the key properties of the world that we may care about for a particular problem, right? So you can't really see in all of these images, but this is kind of like a graphics engine with some kind of physics engine behind it, all right? So a world model coming from the physics. So you can ask things like, if I drop an object, will it fall? You can go into more detail and say, in which direction do the different objects have different masses, and does that impact how they fall? And you can start to queue up complex scenes to the point that you eventually end up doing things like simulating fluids, which is obviously notoriously extremely difficult to do. But the whole point is that none of these are the world, right? We're not simulating everything down to quantum mechanics. At least I hope we're not. We probably can't even do that. We don't know that yet. But somehow we are still able to build a world model, all right, or a physics model, even if we don't understand all of the details of physics. And that's the kind of whole point of this, is that if you enter into a level of abstraction where you have enough control, you can make a good approximation of the problem. Okay. And so we're going to be looking and discussing how to do these kinds of things for language. Okay. And so the intuition is the exact same. The only difference now is that our notions of what an event is. So instead of something falling over or, a carriage on a train, you're now going to be talking about the pieces of language, right? So we're going to be talking about tokens or text or symbols or sentences and how you put those together and how we're going to make something that can predict the events or the different sequences of language that you may see. Okay, so language models estimate the probability of different linguistic units, and then you are able to use that to simulate the creation of language, right? Is it the exact process that humans are going through to create language? Probably not, right? We have far more complicated things in our brains. We have, different regions that are involved with this, but we can still do something like a crude approximation, right? We don't need to understand quantum mechanics to simulate physics. You don't have to understand the inner workings of all aspects of our brains to understand how we may produce language, right? And we'll see a small example of this in a second. Okay, so language models are everywhere, right? They're in completion text in whatever form they may be. So when you type into Google, it gives you a bunch of suggestions for what you may ask next. Same with translation services. Same with autocomplete on your keyboard. All right, spell checker and all of those things. They're all running language models, right? And so a spell checker will just say, hey, they did something I didn't expect. This is a really low probability token. Cat spelled with two T's. I don't see that very often. Maybe they've made a mistake. Here are two more high probability candidates, right? And that's all a spell checker is just suggesting the higher probability candidate that fits the model of the world better, right? So in this sense, the analogy to extend the physics simulator is the fact that I dropped a block and it went upwards, right? Now, maybe that doesn't fit our model of reality because we know that gravity at least goes down, right? So you can suggest you have something like a model that then says, hey, actually, it seems like it was more likely that it would go down. Maybe you want to consider that world instead. Okay. But the important thing to note is, again, it is an approximation of what's going on, right? So it's not the exact full mechanics of language production and understanding. We will, again, see some of the consequences of this towards the end of the class, which is more of like the modern problems facing NLP and things like that, when we get to kind of like the state-of-the-art stuff. And so what seems like it's going to be easy, for example, separating out those three sentences that are spoken to us, for a human, it can be really easy, and we do understand that really well. But for a machine, they may get confused, right? And so this is coming from this distinction between the fact that it's an approximation of language and not necessarily the fundamentals of it in its own right, okay? So a human can understand that morphosyntax is a word, all right? Because we're given context, we know enough about our surroundings to say that that is probably a single really long word. But then an LLM will hear the same, it won't really know where to separate out. And so it may say morpho syntax or morph or syntax. It may split that word up, that sound up differently. What I do find interesting, though, is that a lot of these problems are also common to humans, right? So if you speak to me in Afrikaans, I know a little bit of Afrikaans. I'm not very good at it. I struggle to separate white space in Afrikaans words, right? It tends to form this one long string to me. Okay, and so that's me not understanding Afrikaans sufficiently to have a world model or language model of it. Okay, and so even if we are looking at these problems, there are usually some kind of correspondence to fundamentals of language learning anyway. And so we hope that our models are doing something informative about reality. Okay, so that's the jumping off points of what a model is. All we're trying to do is be able to simulate something in our environments. In this case, it's language. Okay, so the kind of approach to doing this, the general framework, is that we just want to understand probability. Okay, again, if you're doing a physics model, we know that the probability of a ball going upwards when I drop it is exceptionally low. And so that's the thing you don't recommend happening, right? Same with language. We don't want to see words that appear like they don't belong in that context, right? And the word context here is what matters, because that's what constrains us. That's what constrains our belief, right? If I told you that we were on some planet very, very far away with 6 moons hovering right above us, if I dropped the ball and it went up, now you kind of think maybe, right? Maybe that moon did have a gravity pull that pulled the ball up. So there is context and necessary information. And what is also a problem is the fact that a lot of the time that context is assumed. For example, I told you the ball went down. We all assumed that I was on Earth, right? The same applies to language models. If it's not in the context, it usually then has to be assumed by statistics. And then it becomes a question of sampling, and we'll see a problem with that towards the end of today's lecture. Okay, so let's get the fundamentals in. So what is the probability of picking a green ball? Well, we've done something like this before when we discussed softmax. And so it's 5 divided by 18. Does anyone remember what the word I gave for 5 is? Sorry, that's a really hard question to phrase. Okay, what is 5 divided by 18? It's the probability of the green balls. So what was the number 5? Yeah, correct. There we go. That's not everyone uses that word, but Bayesians like it. So correct. It's propensity. All right. So the number 5 was arbitrary. It was the propensity of it. And the way you go from propensities to probabilities is to divide by the sum of all propensities. In this case, there were 18 balls. The same is true of language. Okay, so ideally, what we would really love to do is define a propensity for a sentence and then divide by all possible sentences we could have seen. And then I can tell you how probable it was to see that one sentence. The big issue, though, is that language by design is what we call compositional. And so you put pieces together and you can create an infinite number of them or a near infinite number of them. That's kind of why we like it, is because it gives me the ability to do many cool things with my language. The problem with that many's in a sentence is the fact that almost all probabilities are going to go to 0, right? It's very difficult to now predict how probable any one sentence is that another person is going to say, okay? And so with this approach, the sentences that never occur are all given 0 probability, and almost all sentences are going to be 0 probability, even if they're a little bit reasonable. However, if I showed you those two sentences, all right, so I'll read it. So the mut is timning the tebben, and mut the timning tebben is there. Which one sounds more reasonable, and which one sounds like Star Wars? There we go, right? Because it seemed to fit the structure of a sentence we've seen before. Okay, and so there is the ability to do something like understand the structure of language, even though mat, timning, and teben are words that I do not understand, right? This at least fit the subject, verb, object structure we know of language, when the one at the bottom seemed to not, okay? And so what you just did is you ran the language model. And so even though you haven't seen the sentence, you were still able to say one of those things is more likely than the other based on the full knowledge of language that you have, all right? And that's the type of thing we want to now start embedding into our models, is an ability to do something like inference, even if these words are not seen. And so that's the problem with doing count-based probabilities for this, is that they are not very good at inference, okay? So we cannot treat sentences as atomic units. We have to do something else and start getting smarter and smarter about how we do this something else. So the first step is to try and define probability in terms of its pieces, all right? So we'll try and define the probability of a sentence in terms of its pieces rather than as one whole unit, okay? So formally, let's say that the y's here are a sequence of tokens, and then we can define the probability of that entire sequence, right? So again, what we don't want to really be doing. So what we're going to do instead is we're going to decompose this into the product rule of probability, also called the chain rule of probability, which just says that I'm going to treat each probability in isolation and then try and separate them out. Okay, so I'm going to say what's the first word in my sentence and how probable was that? Then given that I've had that first word, how probable is my second word? Given I've seen 2 words, how probable is my third word? And so mathematically, this does then start to collapse back onto that joint probability with the general formula that I'm just multiplying each of the individual probabilities of my next word given all of the words that came before. Okay, and immediately you should be starting to think about last week's lecture, hopefully, and you're like, hey, Devin, I've seen this before. Didn't we solve this with recurrent networks? Didn't we already have this issue of trying to keep track of memory? And it's fantastic. You can actually just leave the lecture if you thought that already. Okay, that's all we're going to do today is essentially build up a recurrent network argument for what we're seeing. Okay, and so what we're going to do is go from left to right and try and model the probability of each word. Okay, this is a standard framework. It is not fundamental by any means. Obviously, some languages do go right to left and so on. And so we're going to have to generalize this as we go. All right. And the only difference then is how models differ in the way that they resolve or evaluate these probabilities. Okay. And we'll see a few more of those types of things later on. And so we need to define that probability. All we need to do is say, well, how do I state what the probability is of a next word given a sequence that came before? And in terms of our current language, and I want this to be really clear because it is slightly different from word to vec, this is called our context. Okay? So the context is all of the information that we've seen before that we know that can help us predict the future. Okay? Same analogy. Same analogy in our physics engine. I gave you the context that I was on a planet where there was enough gravity to pull the ball out of the world. Now, when I drop the ball, you can predict what happens next, which is it goes up. But that's only true in a specific context. Okay? And fundamentally, a lot of the ideas of language models these days is to just show such enormous amounts of information and context that it becomes almost impossible to not say the right thing. Okay, that is a very fundamental belief behind what we're doing in modern LLMs. Okay, so we're going to look at two of them, Ngram models, which is a counting-based model, and then the neural model, which I think will be the far more intuitive one going forward. So I always like doing this with every single class because every year you guys get slightly more cursed. So if you're going to humor me, it's going to be slightly fun. What I'm going to do is we're going to play the language model game as each other in this room. So we're going to start the sentence with I, and then you're all just going to shout words and I'll, string them along as I hear them. Then we're going to do a second version, which is where you're going to shout pairs of words and we're going to string that along and see how different the sentence is. Okay, we're all ready. We're going to do it for 2 minutes and then we'll carry on. Okay, so I am, a finished sentence. Okay, there we go. You guys are a finished sentence. That's better than last year. Last year they killed a dog. Okay, so you are all the finished sentence. I was hoping you could say I am the finished product because you guys are getting there. Let's try the two pairs of words one. All right, so I like to go to. There we go, the movies. Cool. You guys are less cursed than last year. I'm glad. I really thought someone was going to say, I like to kill dogs. Okay, so it's the same idea. That's a language model. What you guys just did as a, very big swarm language model is try and predict and string the next word along. All right, so that's exactly what our models are going to be doing. Sorry, Matty? Yes. There we go. Yeah. Okay. And so ultimately what we just did is called greedy decoding. Okay, so you pick the token with the highest probability, and we'll see some examples of that now. But notice how as we went longer into the sentence, it became clear where it was going or what we wanted to do, right? When you said full stop at the end there, that was really good because that was very in line with what we had just said before, right? That sentence didn't have many possible paths to go from where we were. And so we said full stop and we ended, all right? EOS token was the LLM version of that, but, EOS. Okay, end of sentence. All right, so how do we get the model to do this so we can compute this big probability? You need to find that individual probability, and so we're just going to count it based on a really, really big corpus. Okay, the same exact idea as green balls, except for the fact that now at least we're counting words and we're not counting necessarily entire strings on their own, entire big chunks of text. Okay, there is an almost here because we're going to use one key or two key aspects to make our lives slightly easier as we go forward so that we don't get these zero probabilities in our model. Okay, so there is a straightforward way, which is just the fact that if I want to know the probability of seeing a next word YT given T minus 1 words that came before, so given my context, what's the probability of my next word? Well, it's how many times I've seen that full string up to the new word divided by the number of times I've seen the string that came before it. Okay, So given the set of sentences that start with this particular way, all right, Devin says he loves, okay? You count the number of times you've heard a sentence talking about Devin loving something, right? Now what you're going to do is you're going to go and count the number of times Devin has loved cats, okay? How many times of that set of sentences that start with the first T minus one words, how many times did they end in the teeth word, right? And so in this case, you've heard me say that a lot. So maybe you've heard me say that sentence 10 times. Devin says that he loves, came up 10 times, and 8 of those 10 times I ended the sentence with cats. All right. So now it's an 80% probability that you're going to see the word cat next time you hear me start the sentence in the same way. All right. Basic kind of count-based frequentist probability. The only problem is that these are often really, really long still. And we just said we want to get away from that, right? So yeah, we're not now just saying, well, what's this giant joint probability of all of these words together? But we're not doing much better because I still have to do some kind of giant joint probability of one word less, right? We haven't really made a ton of progress. And what's really bad is you'll see that that is a divide by zero if I've never seen that start of the sentence before, right? And so now you're going to get something that's just completely undefined. So we need to get a little bit of machinery and tooling to try and figure this out. And the first bit is called the Markov assumption. If you've been taking Giroux's RL class, you know what the Markov assumption is. And it is essentially just going to say that I do not have to consider an aspect of the past, right? In reinforcement learning, we usually say I don't need to consider the past at all right? So as long as I know the present moment where I am, I can make good decisions for my future. I don't have to care about how I got there. In language, we do have to care a little bit about how I got there, right? It's not just about me knowing the exact state or the exact word. I do need a bit of context, all right? But I don't need all of it. I don't need to go through the entire book of Harry Potter just for me to predict the next word that's coming up in chapter 20 when he's at the Triwizard Tournament being chased by a dragon. All right. You maybe just need to remember up to what's happening in that scene to predict the next word. And it's the same rough idea, right? We're going to define something like a scene length in our text, which is the bit of tokens that I care about. So you'll notice here that instead of starting at index 1 over there, it starts at t minus n plus 1, which is just going backwards n minus 1 tokens. All right. So you don't go back to the very start. You don't go back to the first word you saw. You just go a certain window back in time and do the counting that way. And so how many words we use depends on whether or not we're calling it a trigram, a unigram, or a bigram. All right. So if all it's doing is predicting word probabilities with no context, then it's a unigram model. All right. If you have one word of context and then you're predicting the next word, there are two words being considered. So it's a bigram, bi for two, and then two words of context, one word predicted is a trigram. All right. Please don't get that mixed up. It's the kind of thing in a test you say trigram and you mean bigram or whatever because you now can't remember whether or not this word is counted in it or something. It's a silly thing to get the words mixed up. I try not to test that sort of thing, but sometimes it comes up. I can't always control it. And so just try keep that in mind. That's a little bit of a wordy thing. That trigram or the n of the gram does include that last word. All right. And so what we're going to do is say, I saw a cat on the mats. And sorry, I shouted. I saw a cat on the mats and I need to predict these probabilities. Well, if I'm doing the full version of it, then I need to say, what's the probability of starting the sentence with I? What's the probability of seeing the word saw given that I said I? What's the probability of A? Given that I saw the phrase I saw a, what's the probability of cat? And you can see that I'm already getting bored trying to say this. And by the end of the sentence, it's really long. You have to say, given the fact that I saw a cat on a, what's the probability of the next word being Matt? And on top of that, if you're really going to be trying to estimate multiple sentences, you have to do this over and over and over for all of them. And so what we're going to do is just say, never mind, I'm just going to keep track of the last three words, or the last two words, so I'm using a trigram. All right, so a 3-gram, you can always write it that way as well. All right, so I'm going to use a 3-gram, which means I have two context words predicting the next one. So I will still say what was the probability of me starting my sentence with just the probability of that first word, P of I. Then there's the P of I saw. All right, so 2 words. And then now we're reaching the length of my context window that I care to hold on to. So what, given the fact that it's I saw, what's the probability of A? But now we've gotten to the full length. And so instead of considering all the way back to the first word in my text, I'm only going to look back 2 words. So considering that the last two words we encountered was saw what's the probability of cat? All the way down to the bottom one, instead of saying I saw a cat on we're just going to say, well, I'm just going to consider the fact that it said on all right, and I'm going to pick a word. So maybe the fact that it's a cat has now fallen out of my context window, all right? Maybe it's the fact that I was watching, I don't know that I saw. All we're now saying is that given that something is on I need to pick a noun so that it still makes sense, all right? So you may say, I saw a cat on a car, or on a mat, or on a moon, right? Like that, we don't now have any way of really hanging on to that full context, but at least now this is computationally a little bit easier to do. All right, you can start to see the problem, and I'm sure you've all encountered this with LLMs, when something starts falling out of the context window and it starts saying things that are a little bit strange, right? It's because it just doesn't know that information anymore. I see now a lot of the LLMs will try and summarize the text before, okay? That's one of the strategies to shrink your context window, but while maintaining all of the important information. All right, so this is still a fundamental issue, even if we are getting really, 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 really clever about how we handle context, okay? But now when I want to come through and say, what is the probability of the next word? So we're saying mat, we're going to take into account a cat on a. So this is a 4-gram in this case over here, 3 context words plus my new word. And so all we're going to say is, well, how many times did I see a sentence that said cat on a? And how many times did that phrase end in mat? All right. Obviously, this set is going to be larger than that set. Okay. By definition. All right. So there's no chances of us getting a greater than 1 probability in this case. And so we don't even have to do something like an exponential here if we don't want to. All right. But we still have the 2 fundamental issues we pointed out earlier, which is the fact that I can divide by 0 and I can have a 0 at the top. All right. What's the problem? We're going to just do this for ourselves. What's the problem with having a 0 at the top when I need to keep stringing these along? So maybe the next thing is cat on a mat. And then here we have probability of mat given cat on a. All right. So I want the probability of my full sequence. Dot for full sequence. All right, I have the probability on the left of my full sequence, and I'm decomposing it into each of these 1-word probabilities with a Markov assumption to make it a 4-gram. What is the problem that we're going to encounter here? We're seeing a 0 in the numerator. Yep. There we go. The minute I get a single word that I've never seen before, I will now think that that sentence is impossible. Correct. Thank you as well. I assume you're going to say that. All right. And then the same thing is a problem at the bottom. We're trying to string along these counts of the number of times I've seen the words. But if I get to even 1 phrase that is now unseen, I'm dividing by 0. And so that's actually just an impossible thing to really get around. And so we're going to have to just try and have some sort of prior over it. Yes. Correct. Yes. Right. So that's kind of adding the prior, the uniform distribution across all phrases. The problem again is that if that's what you've done, you're going to have a prior that is very low but uniform, and so it will still start to dominate the probabilities. Okay, so picking this really small value, even though it's really small, does actually end up kind of really dominating your distribution. But yeah, that's maybe the best thing we can do for a count-based approach to language. Language is not inherently count-based. Okay, the one other thing we can do before we start adding regularization to this is a kind of to try and say, well, I'm going to do as much as I can to count this probability. All right, so this is known as back off or stupid back off. Essentially, the minute I run into a problem like this, I just reduce the size of my context window, which means that my probability can only go up. All right, because again, the longer the context, the more constrained your sets of possibilities, which is usually a good thing if you end up getting one really clear winner. But if you've over-constrained yourself, then you get no possible candidates. And so all we're going to say is, okay, I constrained my context too much, my bad. I'm going to have a slightly bigger amount of probability. So I'm just going to make it even smaller, right? I'm going to give myself more flexibility in what I can say comes next. Okay, So for example, at the top there, if my count of cat on A is giving me 0, so I've never seen that phrase, well, maybe I should then just try and approximate it by only considering on A. So how would the sentence end, even if I don't care that it was a cat, right? Maybe it's anything on A. And again, we see the problem with this. Your context window has gotten smaller. We now don't have so many constraints on the next word, which means that we're going to be more unreasonable. But hopefully in this case just makes us able to compute something, because I may not have seen a cat on something, but I may have seen a dog or a towel or a squirrel or some other kind of noun on something. Okay, and then even if that doesn't work, if I'm getting 0 probabilities for on A, then I'm going to try and just take the probability of A, right? So maybe I didn't see anything on it, but I've now seen the word A followed by something else. So a mat is now something I've seen in my dictionary or in my training corpus. And so maybe that can help me. And then finally, if I've never, ever seen that context in my life, I have no possible way of engaging with it, I'm then just going to pick randomly and say, well, what's a really likely word? Given my dictionary of words, what's something that's really likely? And you guys did this as well, right? When you were making your string of sentences, what was one of the first words you said? You threw out the word the. All right. You said, I like, and then you said the. And the reason we went that way is because we didn't really know what to do after the word like. There were too many possibilities for us to do. And so we just threw out the most common one. All right. Doing things like articles, a, the, and those kinds of things, which is why you see LLMs to this day still do that as well. They write these really long sentences and they keep throwing out articles to keep themselves going because that looks like it's high probability. And then every now and again, when the sentence gets long enough, the statistics of ending a sentence just outweigh the statistics of stringing together a new article. And so they eventually just say, okay, end of sentence token. All right. And again, we did that as well, to be honest. Okay. So that's stupid back off. And we can be slightly smarter about it, but still, even then, there's now all we've done is taken something algorithmic and made it a hyperparameter problem. And so what we're going to say is, okay, I'm just going to take all possible n-grams up to a certain size that I care for it to be. And again, that's going to just be a choice. So in this case, we're going up to a 4-gram model. Could have gone 5-gram, could have gone 10-gram. It depends how big the data set is that you have and how likely you are to get those probabilities. And then the minute we encounter a 0 division, you just don't use that probability. And then everything else is just picking these lambda values that have to be summing to 1, all right? So it's an interpolation of the probability, all right? If it doesn't, then obviously this doesn't become a probability. So this is just keeping the entire string as a probability. Okay, and then all you do is linearly interpolate, all right? So if you can define Matt as a probable thing given cat honor, then lambda 3 is going to get some high probability. Otherwise, you set it to 0 and lambda 2 gets a high probability. But now at least you always have some kind of contribution from just how likely a word is on its own as well, which can help you kind of guide the text, right? It means that you're more likely to sample things like articles in your sentence. All right, so there's at least one way to do it, but now you have a problem of how do you pick the lambdas. It's again a hyperparameter optimization problem. And so you can do something like cross-validation. You can take should be given all of what you have and which gives you the best task performance and which is the best predictor of the next word. But again, it is then based on just picking from a subset of your data and using something like a validation set. Okay. The other alternative is exactly as we said earlier. This just comes from naive Bayes. You just pick a really small value and you add it to every single thing you could see. So that's the cardinality of your vocabulary over there. So every possible word is slightly probable, all right? There is no sentence that has 0 probability in my mind. I could always just throw out random gibberish and that is still possible. And so every word has a really small delta probability. And so when I'm now trying to consider one individual probability, that's a single delta on top, divided by all possible words it could be, which is then that divide by the cardinality of words at the bottom. Okay, that's great. It works exactly like a uniform prior in a Bayesian sense. So that's really good. But now what we have is essentially a divide by like 1,000,000. All right, that's sitting right in the front of all of our probabilities. And so we're now not exactly really going to help ourselves because we're just going to pull every probability really low down. Okay, so we want to be slightly smarter, but maybe for the case of counting-based methods, that's the best we have. And they did get us really far. That works fairly well, right? So here's some examples of text. I'm not going to try to read all of them, but when this option may be the worst day of Amnesty International delegations visit Israel and felt that his sisters, that they are reserved for someplace concentrating factory. You can see that every word kind of makes sense given what it's recently seen, but across from the we're going to see a problem similar to this at some point in the near future where language models actually start doing a similar thing. And it's a kind of looming issue for large language models. Okay. I will leave it to you guys to read all the examples. Okay. So we have 10 minutes and we'll take a break. So let's just keep chugging along. So we did the count-based methods. We saw a whole bunch of problems with them. That's the classical approach. Obviously, now we are big into neural networks. And so can we use a neural network to do this? And, we've already seen one or two architectures. We saw CNNs, but we've already seen one architecture that's really, really good at adapting to different sizes of contexts, which is the RNN. We just saw it as a classification problem where that was something like named entity recognition or a sentiments analysis or producing ratings on a movie or a description or something like that. We haven't seen it produce language. Okay, and so that's the only generalization we're going to introduce now today. Okay, does anyone have any questions? We're all following. Cool. Guys online, are we happy? Cool. Okay, so the general view still holds true from last time. We have some kind of representation of our words at the bottom here. They are going to be giving us embeddings. So the words at the bottom, we found out last time that they could also be tokens. You can take something like BPE and all of the little symbols you get from BPE then become tokens. So we have a way to have at least an open dictionary. All right, we can combine words together at some point. But for now, again, tokens and words, we're going to treat as synonymous. So we understand, hopefully to a degree, something about the words at the bottom. We have them individually embedded. All right, pre-train them, take them from a word to vec, take them from a word to vec, and then still train them now. You can do a whole bunch of flexible things like transfer and so on that we spoke about a bit last time. All those same ideas hold true about the tokens at the bottom. And just like last time, we're going to shove it into a neural network to try and give us out a single vector representation that we call H. Okay. And so what we're doing is we're taking the meaning of our words from our embedding space and producing a meaning of a sentence at the output of the neural network as best we can, with meaning being defined mathematically as predictability of next word. Okay. So we're going to process the context. This is all model specific, and you're going to get a vector to represent all of the previous context that you have. And then we're going to evaluate the probabilities of all of the next words. And that's the only thing that's changing here, right? Is this output from the neural network. So given the embedding of my sentence, given this H representation, we're now doing a big classification problem. The only thing is that we're now not just predicting one of 5 categories. We are predicting over every single possible word we could see next, right? It is a really, really, really big classification problem, okay? And so you have the cardinality of V. So V is our dictionary or our vocabulary. And so cardinality is the number of elements in that set. Okay, that's all we're going to do. And it's the exact same thing we saw last time, just with a bigger problem. And that's exactly what you can see here, right? So word embeddings go into the neural network. You pop out with your H vector of the sentence. And so now all we're going to have to say is take this D-sized vector, which is H, and project it up to the cardinality of our tokens. All right, so this is just a big linear projection upwards. And then you're going to run it through a softmax distribution to turn your propensities into a probability. All right, same kind of problem holds though. That softmax is going to be very, very sparse, and it's going to be dominated by a really big context where only a few possible things can pop out. All right, so it's really nice that it can be constrained by the context, but we are always expecting our models to generalize. All right. If there is even a single bit of that context that it hasn't seen before, it's going to have to take the individual understanding of those words, which is great because that's why it works better than the count-based methods, because now at least I can try and reason, okay, reason in a sense, reason about the words I've seen, combine them in some kind of strategy, and again, that's defined by my data. I don't know what strategy that the neural network's going to land on. I'm going to try and interpret it at some point, and it's really important for AI safety at the moment that we can interpret these things. But it has some strategy to define the meaning of a sentence given the meaning of the individual words. Okay? And it is going to have to extrapolate, and it's going to have to try and generalize the minute it sees something new. But it's still mathematically defined, and it can still then hopefully have enough reliable information to just project up into a classification over the next words. And so that's why it works over count-based methods, is because it's doing it a little bit more stepwise, and it's because we're defining something in a continuous space very early on, right? It's not so discrete, it is continuous, and so you can start to at least find something like a vector that can help you solve the problem, okay? The problem with operating in vector spaces is the fact that you need lots and lots of data to try and constrain them and map them out properly. And then if you don't do that, you end up with things like jailbreaks and all that sort of thing, which we'll chat about in a few weeks. Okay, so the simplest way of thinking about this, again, you have your D-sized vector. Okay, what we need is a classification over our categories. And so this is just one big linear, kind of linear projection or something like a multi-class softmax or logistic regression at the bottom. All right, so you're just transforming from a D-sized vector up into the cardinality of your dictionary and softmaxing, as I've just said. So this is looking at it more from like the fundamental machine learning or like statistics way of doing this, where it is a big regression problem. There is obviously the other way that you can look at this, which is to say that, well, when I was doing word to vec, I thought about this as an encoding decoding problem. This looks a lot like an encoding decoding problem, right? Word to vec, I took a focal word and I predicted another word. This looks similar, except the only difference is instead of taking a focal word, I'm taking a full sentence representation, and I'm still just predicting another word after that. Okay? And so that's kind of the idea of how these vector spaces work, right? Is we are now going to learn to decode whatever sentence representation I have on my left in the red, the HT. I am now going to learn how to decode from it to my next word prediction over here. And again, this is why it generalizes, because we know that the dot product is well defined. So if this is my H vector that's pointing somewhere in a semantic space of sentences now, right? All I have to do is try and find a really big set of different V's, or sorry, different decoder embeddings, all right, mapping onto the number of different words I have in my vocabulary, which is a bunch of different vectors pointing in all different ways. Okay, and so even if I end up in a situation here where I have a sentence I haven't seen before, right, that vector is pointing in the red towards the top right, I can still just go and say, well, given all of the other word embeddings I have, which is the one that is closest over here? All right, I'm just going to pick that one instead. Okay, and so again, it's because that we're now in this continuous semantic space that we can start to be more flexible about how we reason over which words come next, right? So we're moving away from that discrete counting-based method, and so because the dot product is just defined in general, we can be a little bit more flexible. Same idea. Again, it's up to you which one you want to look at. Do you want to think about this as a classification problem over the words you've seen, or do you want to think about this as a decoding problem into a new word, kind of picking the words that you want to decode next? Up to you. The field has somewhat chosen the latter, but both work. Okay, now the same thing. All right, we have this decoding out, let's say, and that's defined by a dot product, but the dot product can be negative, and so it's not a well-defined propensity because that means I can get probabilities greater than 1. So what do I have to do? I have to turn my propensity into something that's always going to give me a positive value. So I do the dumb thing. I'm just going to take an exponential, right? Its lower bound is 0, and it's monotonically increasing. So at the very least, I won't change the ordering of my probability. All right. I do change the probability, but the ordering of them stays the same. And so I will hopefully always pick the same word I would have anyway. And then what do? We take the propensities, divide by the total of them, and we get ourselves a probability. Okay. I know I said that as if it was one long sentence, and that was a big rambly bit of text. Does that make sense to everyone? All right. Same ideas we've seen before. All right. You decode onto your vocabulary space. You define your propensity well, and then you use that to get your probability, and that is just your softmax distribution at the end of the day. All right. Clear? Cool. That is exactly 11 o'clock. Let's take a break and we'll come back and we'll talk about training and one or two of the problems of these models. Thanks. I'll see you at 1:15. All right, guys, online, let's get cracking. Can you hear me? Cool. All right, so let's look at how we train this. So obviously, if the thing that's coming out the end of the neural network is a probability, well, then we know that we can label it and use cross entropy to minimize that loss. So in this case, we're going to have a single target output, right? So it's a big vector of zeros and a single one target word that is the one that we actually see in the data, okay? Does anyone want to tell me, if we're thinking about this as some kind of very basic extension of Word2Vec, does anyone want to remind me what the problem is with having a target like that off the back end of it? Oh, okay, yeah. Nathan, can you say it again, please?
Isn't it because of the sparse data or sparsity of the results?
Sparsity is one of them. You'll see now that the cross entropy doesn't really suffer from it too much, but you're on the right track with that idea. Just keep, there was one other problem with Word2Vec, the like fundamental issue of it, really. Anyone else want to? Yep. We do know the context, right? We've encoded that in H now. So Word2Vec, we didn't know, again, that was word to word. This is now sentence encoding to a word decoding, right? Same kind of idea. I suppose it's not really also a problem of Word2Vec. It's the reason it works well as well. But there's some aspect of optimizing this that makes it really hard. Most of you are now annoyed at me because I haven't given you sufficient context to answer. That's like, if you can explain yourself better. So what I'm trying to get at here is the fact that those labels are going to be somewhat inconsistent. It stems to the fact that we have to pick a single label. So it is sparsity, as Nathan mentioned. We have to pick a single label for every word we see, right? We're not training in the distribution of words that could follow from I saw a. Okay, I only have examples of real text where a single sparse word was chosen. Okay, but there are many candidates that can go into I saw a next word. Okay, so you're training a probability distribution over next words by showing it many examples of one discrete kind of labeled next word predictor, right? And so it's that in that conflict, in that inconsistency in the labels, that we eventually are able to learn something like a distribution over the next words, right? And the whole point is that if my context window gets long enough, if I have a long enough sentence, it then becomes more and more likely that my probability is going to collapse around a single word, right? Every time I add a word, it just makes it easier to predict, okay? By definition, having one more word in your context cannot make the probability distribution wider, okay? Because you've resolved more information. So every time I add a word, my distribution is going to contract around the next word and contract and contract and contract. But we are still going to always be in a case where it's very seldom that there's one perfect word to predict next, right? And so we're going to have a distribution over candidates. And this is going to be a big part of what we discuss for the next like kind of 20 minutes towards the end, about how do you deal with that aspect of the inconsistency. Okay, the answer to it is that we're going to do something really similar to Word2Vec. You're just going to train it to be minimize the difference with each word, and hopefully in this inconsistency it kind of pulls out something that looks like a really clever latent space of sentence meanings. Okay, what you will notice is that we are summing over all of the words in the vocabulary. Okay, so you want to make sure it's not putting probability on the zeros, all right, or over here, and you want to make sure that it is putting probability where there is a 1 over there. Okay, the good news though, with this being a whole bunch of zeros in our labels, is that this P star is going to be 0 for every word in my vocabulary. So what this eventually collapses onto is just maximizing the probability of the word we saw. Okay, so if you were worried about the sparsity being a computational thing, at least in this case, the cross entropy works out for us. All right. One thing just to note, not to muddy the waters too much, but just in naming, please keep track of the fact that this is cross entropy and not binary cross entropy, right? Binary cross entropy is the one where you go 1 minus p or p star log p or 1 minus p. Okay, that's binary cross entropy because then you do the both sides of it. We're not doing that. All we're doing is this second bit for every single word here. All right, so it's cross entropy, not binary cross entropy. I'm not having the 1 minus of all my labels anywhere else. Okay, just keep track of that, please, so that we're not getting confused, because that will throw you off in how you train these things. If you try and train these things with the binary cross entropy, it will just break, really. And this is a big issue for most of the times, and maybe not LLMs anymore, but initially this was always something that people used to get caught on, is the way you output the distribution, the softmax, very seldom matched the loss function, and that was like a really latent bug that PyTorch had, especially because PyTorch names their loss functions really weirdly or sometimes unintuitively, right? So you'll get binary cross entropy from logits, and you'll go and use that when what you really wanted was just vanilla cross entropy from the softmax. Okay, so keep track of that, can be an issue. So that's how we're going to train the labels, right? So again, you're going to have it predicting one word, so it has to put a probability distribution over which words it thinks is likely, and we're just going to show it millions and millions and millions of examples of sentences, so that it eventually figures out what the distribution over next words is. All right, and so now all we have to care about is how do I get that encoding of H in our pipeline. All right, so I abstracted it away up top here. All right, we've just been looking at this piece over there. All right, well, including this. So now I just need to tell you how do we get this H vector, and it's the same exact way we got the H vector when we were doing classification. This is just a big classification problem over my vocabulary, the same way that you would have classification over the set of possible sentiments or ratings of a movie or something like that. Okay, so it's the same idea. You're going to have each individual representation of your different tokens at the bottom. They're in a vector space. Vector space means that at least we can interpolate and generalize when we see new things. So hopefully this means that my model can at least generalize to a degree when it sees a new sentence. It's not stuck by the discreteness of our counting. Okay, and so what are we going to do? We're going to have a representation of an initial token. One thing you will note now is that at every single step, it has to predict a new word, right? So in the past, what we were doing is we were just kind of ignoring all of that. We were just going to read in a word, update it, and then try and use the recurrence to pull it forward. Then we would get my, let's use blue. Then we would get my next word. We would do a projection into the big sentence space, try and combine it with what I saw before, and you would get a new updated representation of my sentence. Okay, then you'd see the third word. This you understand in isolation from the embedding. You try and project it into your sentence space and combine it with what you saw before. And so you have this running tally of all the kind of previous words, and you can hopefully understand your sentence. What's happening now with the language model is that we are predicting the next word every single time, right? That's what makes it a language model. You don't just say you have a model train because you produced the steam engine at the front, all right, or made something that looks like a steam engine at the front. You have to do all of the carriages along the way, and you have to be able to predict all of that as well, all right? And so you start off by saying, well, here's a random initialization, all right? What's going to be projected off of it? Well, you're going to do what we did when we started that. You're just going to predict an article or some word that's really used often at the start of a sentence. Then you feed that back in, right? It's important that you feed it back in so that your model knows what it's already said. Okay, so that's all we're doing here is reminding it of what it already said, giving it a representation of that word so that it can then start to do this recurrence and predict the next word. Then you tell it what it's already said before, updates both of those words, and you do your recurrence so that it can predict the third word, and so on. Okay, so it's the same exact architecture as last time, except you are just treating every single step as a time to do a classification, right? It's the same idea as if I did sentiments analysis, but I was predicting the sentiment every single time I saw a new word, rather than just waiting to see the end of the sentence. Okay, there is a really good aspect of recurrent networks here, which made them better than CNNs, which is why I'm not going to teach CNNs today. but it's important that we know this, which is the fact that the recurrent network, because I have this vector, okay, every time I produce a new word, all I have to do is add that word to the embedding and project it forward and combine. Okay, so it means that I don't have to go and recompute everything up to here before that. That is all summarized by that single latent representation, that H vector that I've already got before. So I have that memory and I don't need to go and redo compute. The CNNs do not have that. All right. So if you were going to do a CNN, what you would have to do is take in this sentence here. Okay, I saw A. You do a full forward pass of your CNN. You get to the end of that with now this kind of long set of kernels. You do your max pooling over the entire sequence. You get a representation of I saw A, and you predict the next word. All right. You see I saw a cat. Then you're going to have to go into the back into the sequence, add the word you just produced, and say, okay, what's the next word from there? And you're going to have to go and run the convolution across that entire sequence again. All right. And so you redo a whole bunch of computation because now you're running the kernel on I saw A. All right. You did that last time. You know what your kernels are. But the problem is you now have to do that so that you can go and do the global pooling. All right. I see your hand. You go to the global pooling so that you can predict the next word after that. So the recurrent network has this kind of really clear, explicit memory, which makes it easier to just keep adding words as you go. What's up?
Predicting what the next word is going to be.
Yes.
Will we get more into like how the large language models work as a whole, like generating responses to text with the transformers?
Yes.
That's more later on that sort of stuff.
I mean, in the next few weeks. Yeah, we're going to very rapidly. But the thing is that this is a lot closer to that already than you probably realize. So this is essentially like a decoder, right? When you're feeding in the words you've already said. All right. A transformer is essentially this with one added computation called attention that you've all heard about. And yes, it is all you need. But then it has this little bit off the front which says that I have some other aspect of language. It could just be, other symbols, let's say. Okay, there we go. And so now you're going to filter that in up to here with the exact same technique. Okay, encoding is when I see all of the sentence up front. Decoding is when I have to predict a word, feed it back in, predict a word, feed it back in. Okay, we will come to that, but essentially it's the same idea. It's a kind of a big recurrent net with a encoder and a decoder. All right. So what we're doing here, every step, I have been speaking about this as if it's a kind of encoding of your sentence up to the point where you predict the next word. But when we move to transformers, we're going to generalize that idea a little bit. Okay. But we'll get there. We'll kind of add our vocabulary as we go along. All right. But the ideas are here. And up until 2020, probably 22. Probably up until 2017, 2018, this was the standard ways to do things, right? Then there was this attention mechanism that was introduced into recurrent nets first, okay, by a paper by a guy called Badanu, who's now quite famous, and I think he now works at Meta or something. And so then that paper revolutionized how RNNs worked, and then eventually someone said, well, I'm going to stop the recurrence and just do attention. Okay, so first things to do is just how do we make RNNs slightly smarter without using attention? And so you can stack them, right? Same idea as the classification. Now at least you have multiple pathways through your sentence. So this word filters in through there, over here, it comes down here. And then when I see my new word over here, it's going to be influenced by what I've seen before in two different pathways, right? It's going to combine in there. And then when it projects forward, it combines in there. So you have multiple levels of abstraction, multiple pathways to update your sentence representation so that hopefully in the same way as like a CNN goes from edges to ears to a picture of a cat, you get something that goes from a simple understanding of things like parts of speech in the first layer to maybe understanding sentence structure in the second layer. And so maybe it can do a similar thing to what you guys did at the very beginning, where I showed you the two gibberish sentences, but the one sounded more like language to you. Same exact idea here. You are learning something like a representation of parts of speech. You are learning something like a representation of the structure of a sentence being subject, verb, object. And that's the kind of thing you can only really do with depth. All right. And so that's why we would now have multiple layers to our RNNs, is it can start to understand language structure in that second layer. If you look at your project, it's one of them is about a thing called an induction head. That's a mechanism that can only come about in a transformer with 2 layers of attention. Okay, it's essentially corresponds to a go back in your text and see what came before and copy a pattern. All right, it's essentially a very foundational way of how they work, especially when they're coding, right? Like you can say, how do they seem to understand names or generalize to variables and stuff? It's because they have this thing called the induction head, which allows them to copy patterns from the past. Okay, they also use it to bypass reasoning to a degree. So same idea, okay? We stack computation to give ourselves more sophisticated processing abilities. And so layer 1 will give you parts of speech. Layer 2 will then understand sentence structure as a result. Okay, are we all happy for now? We're all moderately content that we can learn this the night before a test? Yeah, cool. Okay, there is one big issue with this, and this is foundational, all right? So transformers seem to get around it, but really the reason for this is because we're just throwing such immense compute at it. And there was actually one point I wanted to make about the CNN versus RNN thing. Again, what you will find in NLP is the fact that the most deep mathematical thing doesn't always work, or it's not always the thing that wins. What wins in NLP is our ability to train quickly with very little memory footprints and see tons and tons of examples. Okay, so the CNN had this problem where I had to redo work. So the RNN ended up being better, better because I could then hold on to memory that I keep updating. And so I didn't have to recompute previous words. Okay, I could do it in this rollout fashion, whereas the CNN has to read everything at once. So that was why RNNs were popular for a while, is they could just churn through text far quicker. Okay, they have their own issues we discussed last time, which is the fact that there's a bottleneck and so on, and a credit assignment problem. Back propagating through the recurrence is really hard, but we could at least do it quick enough and show it a lot of data so that maybe it started to back propagate that signal properly. Okay. And the same idea for transformers. Eventually, they just ended up being far, 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 far quicker than RNNs, which meant we could show it so much more data. We could show it the entire internet's worth of data if you had the compute for it and the time and the money. And that's exactly what happened. And it turns out that worked really well. Okay, but we now have one problem with our language model, right? So we're going through every time we get to a representation of our sentence, we have to predict the new word. Then we feed that word back in. Then we predict the next word. So what was one of the problems that you guys had when you were predicting the language that we were doing earlier, right? What was something that made it difficult for you to predict the next word? There we go. But also the fact that you were constrained by what someone else had said before, right? Someone said the word like early on, and now you had to be on topic with that. You couldn't take the story in the way of describing Harry Potter anymore, because you had to now uphold but to talk about something you like. All right. Sorry to Harry Potter fans, that wasn't an intentional example. But you see what I'm saying? So now you predict a word, you didn't have a lot of context to start. So it was a very uncertain, big sampling process that you just randomly threw out a word, but now you have to go and use it, right? And so that gives you the idea of coherence. Okay. Once you've said something, you have to stay on topic, and that's what we want from the model. And the second thing is diversity, right? So even though you may have this big sampling problem, I don't want it to always pick the same word, right? And we saw that happen as well, right? We got to something where we didn't know what the next word was, so we said full stop, right? That is not going to give us a very diverse sentence, because now we have these short sentences that the minute they fit the shape of subject, verb, object, I stop. Right? I like the cat. All right. Full stop there is far, far, far more likely than saying the word like and or except. Okay. But human language communicates stuff, right? We are going to say something like, I like the cat and the dog, or I like the cat except when it scratches my couch. You know what I mean? Like we are actually communicating something with it that isn't just what is the most likely next token. All right. And that is why there was this problem early on, and you can still actually see it sometimes, where language models produce these really short sentences, okay? Because the minute you fit the structure of a sentence, you're really, really likely to just stop, right? That's the most probable thing, okay? And so it comes from the fact that we are using this distributional hypothesis from the beginning, right? We're assuming that language is, or the meaning of words and ultimately the meaning of sentences is defined by what can come next, okay? And that's all we're trying to do is see examples of what can come next and be coherent to that. The problem is that what's coherent to a lot of text is something like full stops and being really short and snappy. And so it becomes quite useless, or it doesn't at least follow the normal human cadence and way of speaking. All right. So those are the two trade-offs that we have in front of us. So coherence says that the generated text has to make sense. It has to be consistent across time. And then the diversity says that it has to produce different samples. I don't just want it to say full stop the minute it said something even remotely close to a sentence. Okay, and the way we get around this, at least initially, is called temperature. So the whole pipeline of this, that again, we're going to see this pipeline over and over for the next few weeks as well. The whole pipeline is that you take in these word embeddings, you get a sentence embedding somehow from a neural network, and then from there, you're now going to map out onto the dictionary that you have available to you and classify what you think the most likely next word is, all right? You're going to decode another word. The way you do that is by getting the product with these vector embeddings of your words and then running through a softmax. All right, you have some propensity there, you have some power to define your propensity. And so what I'm going to do is I'm going to say, well, I don't like this dot product thing, and I don't like this exponential, because what it does is it really favors, let's say my sentence embedding is pointing out there, and I have two candidate words, one like that and one like that, right? It's going to favor this green arrow on the right-hand side because this dot product is really, really, really close compared to this candidate word over there. But that second candidate word on the left may be entirely plausible, okay? And so what we're going to say is that I want to reduce the way that this dot product is so winner-take-all about things. And so I'm going to add more variance, or I'm going to have a higher or lower temperature, okay? So again, I define propensity. I've already defined it as a dot product and then realized that that doesn't work very well. So now all I'm going to do is say, well, it's a dot product with a division and then the exponential. And so what this does is that when you put that tau in the exponential, right, it's going to smooth out your distributions when it is greater than 1. All right, so when tau is greater than 1, what this is essentially going to work like is a multiplication by, once it there, it's going to work like this, exp 1 over tau. Okay, and so when it's greater than 1, that exp is going to start to look smooth, and it's going to look more like a prior that is a uniform prior over your distribution. Okay, it is very, very similar to that idea of adding a delta value in the count-based methods. All right, it's extremely close, if not the exact same thing. All right, all it's saying is that I want to distribute my probability wider across my vocabulary than one winner-take-all kind of thing. Okay, and so when temperature goes up, variance goes up, you're more chaotic. It's a very physics kind of consistent thing. And if your temperature goes down, you're in a colder system, and so you're going to collapse more around one probability. Your probability is going to become more peaked than it was. Okay, and it's a way for us to now at least control between having a high degree of variance in the words we pick or having very coherent sentences, because we're always picking this one really probable word. Okay, and so the way it works is essentially just get your dot product over here and then divide everything by the same constant tau, and that is a hyperparameter we are picking. Okay, so this is just in the slides for your own playing, but there's a nice, on the Lena Voita website, there's a nice little tutorial here where you can go and slide the temperature along, and you'll see how it changes the distribution over words. Okay, but let's look at some examples, get some intuition. So if I set the temperature equal to 2, all right, so temperature equals 1 is the default. That collapses back to normal softmax. So if I set the temperature equal to 2, you end up with sentences that say, Paradise Sits Farm started paint hollow almost unprecedented decisions, care using withdrawal from rebel sys, saying graphics Mongolia official line. All right, really, really, really unique sentence. Very, very, very diverse. That's probably a brand new sentence in the history of humanity, but it also didn't make tons of sense. All right, so you can see another example. Believes transactions article remain considered Britain holding presidency, which had fled profit. So again, it's slightly coherent. It's saying words like profit or presidency following Britain or holding. So it is being consistent to a degree, but it's very, very random in what it's picking. Same for there. If I set the temperature to be less than 1, so 0.2, we're in a quote colder system. And so now what it's going to say is the first time the 2-year-old old girl with a new version of the new version of the new version of the new version. Okay, so from what it saw at the beginning, the first time said that, oh, actually, this sentence really wants to speak about the new version of something. I'm going to say that over and over and over, that the new version is just a really likely word. Okay, the first step is to be used in the first step end of sentence. Thank you very much. That's very, very true. Not unlike the example we produced today, but again, we don't want to just pick EOS the single time we say something that sounds remotely like a sentence, right? And in this case, it's trivial. You ended up saying something that was probably factually correct, but is just really dumb and didn't need to be said, all right? So this is the trade-off that we now have, all right? And apparently it likes generating the sample a few times over. Okay, the hotel is located in the heart of the city. EOS is another example. And so we have a trade-off with how we pick this temperature. It can help a bit. It gives us a knob to turn, all right? But it doesn't solve the problem, because when I increase diversity with a higher amount of temperature over here, I implicitly decrease my coherence, okay? Going the other way, if I'm going to make a colder system, if I pick a tau value that's lower than 1, I get more coherence, but less diversity. All right, I will say things like the hotel is in the heart of the city, EOS. Okay, neither of which really seem to work in the way that human language does. Okay, so this is a big trade-off, diversity, coherence. Okay, keep that in mind. I do like to, what I will say is this is a really easy thing for me to test. So I do test it. So just game the degree if you want to a degree. Okay, there is another way of doing this though, right? So the problem, one of the problems that we have is that we're not adapting our sampling to how many candidate words we have. Okay, and so instead what we're going to do is we're going to say, given the context that I have, so the dress color was, I'm going to go and I'm going to look at how many candidate words I have in roughly the same probability. So you have red, white, black, pink, blue, violet, olive. There are many, many, many colors, right? I have 20 different words that I could stick there that would make sense as being defined by what the dress color was, right? In comparison, if I'm saying the light was, well, the light was either on or it was off, and then anything else below that is really low probability, right? You're almost always going to be talking about a light switch being on or off. But we have a problem is that in this case, you had a lot of different possible solutions, and here you had just 2. Okay, but the good news is that this is measurable. It's measurable by the sum of the probabilities here. Okay, 90% of my next word probability is sitting in those top 2 words on the right, and only 0.06 or 6% of my probability is sitting in the top 2 words on the left. And so for the left problem, I should sample from a greater range than on the right-hand side. And the way we're going to do this is by just saying, I'm going to take all of my words down to a certain probability threshold, and I will then pick randomly from those top sets of words. Okay, so on the left-hand side, I'm going to go down until I've accumulated 80% of my probability. Okay, that's the set of candidate words, and then you're just going to uniformly pick one. Okay, and in that case, you now do sample olive with as much probability as red. Yes, olive is a slightly more rare color on a dress, but it's not incoherent, and so we allow it. Okay, whereas here, I'm going to stop and I'm going to say 80% of my probability mass cuts off at off, and so I'm not going to consider anything else. I'm just going to pick from those 2 over there. All right, and so this is called nucleus sampling. Check the word here. Yeah. Pick the top P, which is called the nucleus. Okay. And that is still used in pretty much all language models. That is a very common way of doing it. Okay, so now at least nuclear sampling allows us a mechanism for remaining coherent while having high diversity. Okay, the diversity comes from the fact that I'm uniform sampling from my set of candidate words. The coherence comes from the fact that I'm still adjusting the set of words that I have available to me. Okay, if only 2 words are really probable, then it means that only 2 words are going to be coherent in that sentence. And so I'm going to randomly choose between just those 2 words. Coherence maintained. If I have lots of words that are available to me, I'm going to still pick from that set of possible coherent words, but then I'm going to pick randomly so that at least I am slightly more diverse, all right? Pick uniformly from that set of possible coherent words. So it's a little bit more of a, a stage-like process. I find my set of coherent words, and then I pick randomly from them rather than just picking the top priority all the time. You can get kind of arbitrarily deep into these sampling methods, and they are still an active area of research today. Okay, and then the last thing we want to talk about, and again, this is kind of the recurring theme in a lot of what we do, is how do we get some intuition for what's going on and how do we measure or at least interpret these models. So the one metric is called perplexity. So the idea here is that you're going to show the model a candidate bit of text, and you're going to ask it to tell you how surprised it is at that text. Okay, this is still used a lot today. We'll come up against it again in the responsibility lecture and the responsible AI lecture. It is a really good measure. And what also happens a lot now is we sometimes don't just use, let's say, our model that I've trained, my language model, and show it some text and get its own perplexity. What I will also do is I will get my language model to produce text, and I show it to a different language model, and I ask it for the perplexity. So a lot of times it goes both ways now. I can ask my model to sample, get it another model's perplexity, or I can show it text that comes from the real world and ask it for its own perplexity on it. Okay? And all perplexity is how surprised my model is at a piece of text. All right. The problem with this, right, and this is a fundamental thing in this distributional hypothesis, is that surprise is important. Okay? If you were surprised by nothing that I have said to you today, then there would be no reason to be here. Language would have failed us. I would have been a bad lecturer, and we would have learned nothing. Okay? Language is necessarily slightly surprising because that's what it means to convey information. All right? But that is still the only measure of understanding that we have, right? And again, when you guys want to know that you're understanding me, what you're doing is you're trying to predict the next word I'm going to say. And if I say roughly the same thing you were expecting, you think you understand. That is actually the kind of mechanism of how we understand human understanding. So we're doing the same thing, right? You're running through a recurrent neural network next word prediction language model for me and what I'm saying. And if we align on that, then we both feel like we understand each other and we're happy. But there needs to be a level of surprise. And so we fall into the trap of over-optimizing perplexity, and that is fundamentally what language models do. But it's measured very close to your loss. Okay? So the perplexity is defined, let's just get the full slide up here. The perplexity is defined in terms of this likelihood of seeing text. Okay, so the log likelihood of seeing the text. So this is exactly what we've been building out for today. You take the probability over all of your candidate words, you put it into the log, the second log, and then you just sum over them. All right. So if you've seen the log base 2 before, that is essentially a measure of entropy. It's the number of bits you need to represent that information. So what you're saying is how many bits of information do I need to represent this probability distribution? The more bits of information you need, the more informative that text is, the more you might learn by hearing what that text has to say. Okay? And so all you're saying is that across all of my words, how much information was conveyed. That's what that log likelihood of your text is doing. And as you can see, that's actually very close to what we're minimizing with that cross entropy, right? You're taking the natural log of your probability and then taking the negative, but it's the same rough idea. And so you can see that on this side, we were talking about information as if it is something being conveyed. And on this side, we're talking about information as if it's something to be removed. It's error. If you're too surprised by everything I say, it means you don't understand language, right? If you can't predict the next word at all, then it means you don't understand language. So there is this trade-off here, and that is kind of what the problem of perplexity is trying to grapple with and solve. by using the log base 2, but it's the same kind of idea. It looks a lot like a loss function. And so then the full distribution is then just 2 raised to the power of that average log likelihood. Okay, so it's the average amount of information in bits that you need to understand a block of text. The one nice thing about perplexity is the fact that it's bounded. Okay, unlike a loss function, we have a really good sense of what it's going to be in the upper and the lower bounds. And so that's often why it's used as a metric. It's an intuitive loss function. It's not the perfect solution to understanding whether or not your model works. Okay, if you're doing any of the NLP projects with me, you'll know that I've said to you, go and measure perplexity as your, at least the measure of your diffusion model, but it's still not perfect, right? There's another score that people use called the blue score. The problem with the blue score is that it gets lower every time you add a word, all right? Or it gets higher every time you add a word. So the blue score can just be gamed by having really long text. Okay, and then that became a problem, which is why the field moved away from it. It was good for a while when we couldn't produce, more than a sentence. But now that we're producing, entire code bases and pages of stuff, blue score kind of just fails anyway. So we've now had to go back to something a little bit more fundamental like perplexity. Okay, so perplexity is maximized at 1. If the model is perfect and assigns probability 1 to the correct token, then that log probability just becomes 0. So this then becomes 0 up top here for all of your words, and you end up with just 2 to the power of 0, which is 1. Okay, basic probability there, that just collapses in the exponent. And so then the worst case is that if you're randomly guessing and you have a uniform distribution over your entire vocabulary, this is still well defined, right? You're in this probability over here, you're going to just have 1 over your vocabulary. Okay, so that becomes a constant. It has nothing to do with the indices of time or anything. It's just a constant probability. And what do we know about the sum of constants? We know that the sum up to m of a constant value, so m of x, I, is, well, x is constant, is then just m times x. Okay, x plus x plus x plus x, m times is just that product. And so we end up with this m over here. Okay, that cancels with what was meant to be the average. Okay, the m's cancel. And so you end up with just the log, or the power of 2 raised to the log base 2 over your vocabulary, which becomes just your cardinality of your vocabulary. Okay, so at least perplexity does have this kind of lower bound that is intuitive, upper bound, which is intuitive, and it's just how many possible words you could have picked around. So it at least kind of expresses something about the range of possible values and the difficulty of your problem. It is slightly more adaptive to the setting and the task you're in, which is nice. Okay, so you want a perplexity of 1, but you're very likely going to get something closer to the number of words you have available to you in your dictionary. Okay, some other strategies we have to try and make this more efficient is obviously tracking output word embeddings is really, really difficult. If you already have a whole bunch of embeddings here, why not just use those? All right, and so we can do weight tying. We saw that in Word2Vec. You can just reuse the same word embeddings you've seen before and train your model to reuse these weights. Okay, there is a downside to this. Sometimes you do want, especially when you're working in something like a sentence space, you do want flexibility to predict the next word. Okay, there is more semantic freedom in using a different word representation for decoding than encoding over here. But if you're in a resource constrained setting, at least then a representation of a word is still what you need on both ends. And so you can just reuse it, and then you have half the number of parameters that you need to track. Okay, so weight tying, similar to CNNs, can make things a lot more efficient. Okay, and then the last thing we can do is just go and look at examples of generated text to try and interpret our language models. So in this case now, we at least have something qualitative to work around, and it's called, visualizing in some sense. Okay, so for example, if you have a character level LSTM, so LSTM is just a fancy recurrent net, and you've trained on a whole bunch of LaTeX algebra books, then what you can do is also train it on code, and you can come through and you can see what activates different neurons in your neural network. All right, so ignore the fact that it's an LSTM and they're talking about cells. Just think of it as a hidden neuron in your recurrent net. When does it become active? And so in this case, this neuron changed its values as you went from left to right in text. Okay, when it knew that it had to get to something like a new line representation, which sometimes they do, they have to put the new line token in, then what it would do is start going kind of more and more active until that neuron got really active and it made the probability of going next line very high, right? And so these representations aren't just semantic. They're not just what do the words mean. It's not just the fact that a cat is more similar to a dog than a chainsaw. It is things like parts of speech. It is things like, is the sentence structured in subject, verb, object format? It is something like, have I reached the end of my line length? Okay. And we saw earlier, we at least discussed earlier, that if you add depth to your recurrent network, these are the kind of things that you start seeing in those later layers. You get representations that are a little bit more in context of the entire text. Okay. They also found representations for things like when you open and close inverted commas. Okay, so that's really useful because that neuron is tracking whether or not you've closed a bit of syntax that you've opened before. All right, a bit of punctuation that you opened before. All right, same for the coding models. They found neurons that responded when you were inside the condition of an if statement. So you would see if, then it would start tracking whether or not it had said something in the if statement that was sufficient to close that, and so on. They found a whole bunch of really cool neurons doing really interesting things. And that's the point, right? That's why these things can code. Every possible thing that it's doing, every skill that it demonstrates, it has to have a neuron, or at least a set of neurons, representing that fact. Okay? And we spoke a few weeks ago about the fact that if you want to understand what it's doing, you need to be able to decode it from that representation. So in this case, if I have this neuron that tells me whether or not the text it's generating is inside of the condition of an if statement, I can train a binary classifier off of that. All I take is whether or not that neuron is 1 or 0 or close to 1 or 0, and I have a classifier. Okay, and so we can probe the neurons, and that's exactly how these things were found. You can probe these neurons to see what activates them and what doesn't. And then try and do things like interpreting what that means for the model and what skills it has. And again, you're going to see this in your projects to a degree, right? The way that they found the induction hit, this kind of really complex look back and copy operation that's foundational to LLMs, that's still just coming from same ideas of go and see what activated the neurons and when. Okay, and try and figure out what they were doing. And this extends to how we interpret attention, and you'll see that in a few weeks. Okay. So I'll leave it to you to go and have a look at just the remaining bits here. It's essentially discussing that idea of looking at what activates a neuron. The last thing I wanted to mention is on the Moodle, come on you. On the Moodle page, there's 1 or 2 links that I just put stuff up that's interesting. You don't have to go read it. I will never test it, but it's fun to see that in 2024, there was a very similar idea that Anthropic did, where they found that their transformers had a single neuron, which is really remarkable because it's very seldom a single neuron that you could go and switch on. You would just set the activity high and run the sentence forward as if it was exactly the same process as before. And all it would do was make the neural network speak about the Golden Gate Bridge. Okay? There are similar notions in neuroscience. They found a neuron in this 150-year-old dude in the early 2000s that responded exclusively to Jennifer Aniston. It got so bad that people thought it was a fundamental neuron in everyone's brain, like that every person was somehow encoded. Turns out this guy really liked Jennifer Aniston, and he kind of changed neuroscience for a couple of years. And so it's interesting that both of these things are showing up. One thing that is very cool in neural networks, and that there's a lot of work on here, is that when you find a neuron this meaningful, you can use it, right? You can make the neural network talk about the Golden Gate Bridge. They also claim that they found neurons that were encoded or leaning evil. And then they were like, don't worry, everybody, we set those to 0. And then AGI was saved. But there's those ideas, and there's a lot of work in terms of steering vectors and stuff like that that are stemming from these ideas. So if you like even a little bit this idea of interpreting stuff, there's a lot of cool work to be done. Yeah. Yeah.
What do you think you could like realistically start like approaching them more attention building? Like, at what point
do you have a reasonable chance of doing it?
Yeah.
Yeah, now. So making the transformer, so we're going to get to that soon, but the way you're going to code the transformer isn't from scratch either, right? But I would start recommending for both of them, start getting the data loaded and stuff like that, especially for the more kind of responsible AI project. All right, on that, what was it, Swahili text? Make sure you're there. There, you could just go and do a word to vec, right? That was meant to be a little bit more of the approachable one, where it's like depth of thought in terms of responsible AI. So that project is within reach. The mechanistic interpretability one is a little bit, you need maybe a week or two, but latest first week of next block. Good. That second project, though, there's a GitHub that does it. And I really don't recommend going and redoing it. Go just take the GitHub, right? And just start running the GitHub and making sure you can reproduce their results with their GitHub. Okay? I'm not here to test that you can go and redo other people's work. I want to see what you do off the top of it. Cool.
If I just submit the GitHub.
You will get well, no, you'll fail because I did ask you for a little bit more than the GitHub. But if you go and take the GitHub, do exactly what I put in the PDF. Well, no, let's take this to the extreme. You take the GitHub, you take my PDF, you pass both into Claude and say, do this. What you will receive is roughly 50 to 60%, and it's a big experiment to see how well I'm going to be able to detect that. But if you do the bare minimum, me and my markers detect that. If you do the bare minimum, I'm not going to reward you, but I'm also not here to screw with you. If you want to do that and you don't actually care about getting really high marks, then you know you're more than welcome to calibrate your own marks if you want. Cool. Thanks, everyone. I'll see you next week.